All right, today we're jumping into a problem that sat unsolved in the world of quantum physics for decades. And it's a real head-scratcher that all started with a question that sounds almost playful.
So just imagine a quantum particle that's stuck on the surface of a torus, the fancy mathematical name for a donut. Where is that particle most likely to be? Now, that might sound like a simple little thought experiment, but for physicists, this was a genuine, nagging scientific mystery.
And what's wild is that scientists had already figured this out for other shapes. You want to describe a particle on a sphere or a cylinder? No problem. They had the Schrödinger equation for that all sorted out. But the donut? For some reason, that seemingly simple shape was just notoriously difficult. It stumped some of the best researchers for years.
So let's get right into it with Section 1 and really break down why this whole particle on a donut problem was such a uniquely tough nut to crack.
And believe me, this wasn't some forgotten problem tucked away in a dusty corner of physics. As Alexander Schmidt, the physicist who finally solved this, pointed out right before his big breakthrough, even with all the modern work on nanodevices and curved surfaces, a clear, exact solution for the torus, well, it just didn't exist. It turns out the unique geometry of the donut made the math an absolute nightmare. So how on earth did they finally solve it? Well, the breakthrough came from looking at the problem in a totally new way. And that brings us to Section 2, cracking the quantum code.
You're not going to believe where the solution came from. It wasn't some brand new quantum theory. Nope. The key was a mathematical technique developed over 100 years ago by George William Hill to study the moon's orbit. How amazing is that? A direct link connecting the motion of the moon to the behavior of a tiny quantum particle.
The strategy here was just brilliant. Instead of trying to solve the messy equation head-on, Schmidt's method completely transformed it. He used something called a Liouville-Green transformation, which is basically a mathematical trick to simplify the problem. It's kind of like changing your viewpoint to make a really complicated shape look simple. And once he did that, a hidden pattern just emerged. It turned out to be the exact same structure as Hill's equation, the one from the moon studies. And just like that, an impossible problem became totally solvable.
And with that quantum code finally cracked, we can move on to Section 3 and get the answer to our original question. Let's finally take a look at the visual map of where this particle actually hides. Okay, just a quick refresher on what you're about to see. These are called probability density plots. In the weird world of quantum mechanics, you can never know a particle's exact location. Instead, these maps show us the regions where it's most probable we'll find it. So think of red as the hot spots and blue as the cold spots.
So let's start with a perfectly neutral environment. No external forces, no fields, nothing. Where does the particle hide? Well, it turns out it doesn't hide in just one spot. It actually spreads out in these beautiful symmetrical patterns that perfectly respect the natural geometry of the donut. This is its lowest energy state, just chillin', evenly distributed across the whole surface.
But what happens if we switch on a magnetic field and run it right through the whole of the donut? Oh yeah, the situation changes, and it changes dramatically. The particle is definitely not free to roam everywhere anymore.
Just look at that. The magnetic field acts like this invisible force that literally squeezes the probability, pushing the particle and concentrating it in this band right around the torus's equator, the widest part of the ring. It's such a powerful visual of how an external field can completely dictate where a quantum particle is allowed to be.
Okay, so let's try something else. What about an electric field pointing straight from top to bottom? Well, this just completely shatters the symmetry we saw before. Our particle is charged, so now it's going to react to this very directional push.
And yep, here's the result. Just like you'd kind of expect in a classical sense, the particle gets pushed towards the area of lowest potential. The probability maps become totally lopsided and concentrated. That beautiful symmetry is just gone, replaced by these patterns that show a clear, direct response to that electric force.
Okay, so we've seen where the particle likes to hide. But the solution to this puzzle revealed something else, something really, really strange about how this system behaves over time. And that brings us to Section 4, the strange case of time. So when the researchers calculated all the possible energy levels a particle could have on this donut, they stumbled onto something weird. In most quantum systems, the energy levels are distinct, spaced apart. But here, they found that pairs of successive energy levels become almost identical. They get packed incredibly close together. So what? A tiny difference between energy levels? Why is that such a big deal?
It's a huge deal, because in quantum mechanics, the difference between energy levels dictates how fast a system can evolve over time. In a typical system, with those distinct energy levels, change happens pretty fast. But on our donut, because those levels are packed so tightly together, the whole system evolves at a snail's pace. A wave packet, which is just a little localized bundle of probability, changes its shape incredibly slowly. It's like a bizarre quantum traffic jam caused entirely by the geometry of the donut.
This really strange behavior actually points to a much bigger idea, which is what we're covering in our final section, continuous versus blocky worlds. Let's zoom way out and see how the principles we've been talking about apply to completely different kinds of systems.
So check this out. On the left, you've got our smooth, continuous donut world. On the right, you have a blocky world, kind of like a pixelated grid from a totally different study. One is governed by smooth curves in calculus, the other by discrete points in grid math. They seem like they're from completely different universes, right? But they share a deep, fundamental principle.
And here is the single, most important takeaway from all of this. Geometry is destiny. It just doesn't matter if your universe is a smooth curved donut or a blocky pixelated grid. The actual shape of the space itself sets the fundamental rules for how everything, from waves to quantum particles, behaves within it.
And that really brings us to our final thought here. The donut was so much more than just a tricky math problem. It's a perfect illustration of this profound concept. So if the simple geometry of a shape can create such unique and bizarre physical effects, what other invisible rules, born from the very structure of space-time itself, are out there quietly shaping the universe all around us?